In this video, we're going to start learning how to estimate the population mean and the population variance from the sample data. And the estimation mechanism that is going to be introduced in this video is called point estimation. Another estimation mechanism is called interval estimation, which will be introduced in the next video. Let's come back to this situation about the weights of people in a population. Again, the population mean and the population standard deviation are denoted by mu kg and sigma kg respectively. And we let x kg be the weight of a randomly selected person. We let x bar kg be the mean of the weights of the n selected persons. And we have learned that this quantity is known as the sample mean. Also, we have learned that the expectation of x bar is equal to the expectation of x, which is equal to mu. In other words, we can expect that the value of x bar does not tend to underestimate nor overestimate mu. Now let's consider the variance of the weights of the n selected persons. And we let this be sigma square hat. Now we have a similar question. Is the expectation of sigma square hat equal to sigma square, just like the sample mean? To answer this question, we need to perform lots of algebraic manipulations. First of all, we have learned that the variance of n data can be expressed as the mean of squares minus the square of the mean like this. And then for this expression of the expectation, it can be expanded in this way. As x1 square, x2 square to xn square are all identically and independently distributed, these expectations are all equal to the expectation of x squared. So we can get that the expectation of sigma square hat is equal to the expectation of x squared minus the expectation of x bar squared. This expression is now similar to the variance of x, which is the expectation of x squared minus the square of the expectation of x, but not exactly the same. We can further perform a trick to subtract and add the square of the expectation of x bar like this. In this way, this part, the expectation of x bar square minus the square of the expectation of x bar, is simply equal to the variance of x bar. We have already learned that the variance of x bar is equal to the variance of x over n. Furthermore, the square of the expectation of x bar can be simplified as the square of the expectation of x. Because we have already learned that the expectation of x bar is equal to the expectation of x. Now this part, the expectation of x squared minus the square of the expectation of x is just equal to the variance of x. As a result, we can get that the expectation of sigma square hat is indeed equal to n-1 over n times sigma squared, but not sigma squared. In other words, the variance of the sample data will tend to underestimate the population variance. In statistics, if the expectation of an estimate is equal to the population parameter that we're interested in, this quantity is known as an unbiased estimator. Otherwise, it is called a biased estimator. From these results, the sample mean x bar is regarded as an unbiased estimator of the population mean mu, while the variance of the sample data is indeed a biased estimator of the population variance sigma squared. However, this bias can be easily corrected by a simple adjustment. If we consider a quantity s squared which is equal to n over n-1 times sigma square hat, then we can see that the expectation of s squared is exactly equal to the population variance sigma squared. As this original biased factor n-1 over n can be cancelled after this adjustment. In this adjustment of multiplying n over n-1, it is equivalent to divide this sum of squared differences by n-1 instead of n. In other words, this s squared is simply equal to the variance of the sample data by considering the denominator as n-1 during the computation. In this way, s squared will then be an unbiased estimator of the population variance sigma squared. And we call s squared the sample variance. Please note that the sample variance is different from the variance of the sample data. The sample variance is a very specific term of which the computation considers n-1 as the denominator. With n-1 as the denominator, this estimate will be unbiased. Nevertheless, the expectation of s is actually not equal to the sample standard deviation sigma. That means although S squared is an unbiased estimator of sigma squared, S is still a biased estimator of sigma. Indeed, correcting the bias in the estimation of sigma is not straightforward. Unlike what we have obtained in the estimation of sigma squared, it is not possible to find an estimate of sigma which is unbiased for all population distributions. Therefore, practically speaking, we usually use S as an estimate of sigma despite its biasness. Now let's summarize the concepts here. Suppose theta is an unknown population parameter and theta hat is a sample statistic. If the expectation of theta hat is equal to theta, then theta hat is known as an unbiased estimator of theta. Otherwise, this sample statistic is a biased estimator. Now the population parameters that we are interested in are the mean mu and the standard deviation sigma. Also, we use x bar to denote the sample mean and s squared to denote the sample variance. In this way, s refers to the square root of s squared, which is known as the sample standard deviation. From the previous discussions, we know that x bar and s squared are unbiased estimators of mu and sigma squared respectively, while s is a biased estimator of sigma. Such a mechanism of estimating a population parameter by a single quantity is called point estimation. In the next video, we will learn about interval estimation, which involves estimating a population parameter by a range of values. Now let's take a look at two examples and see how we can perform point estimation from the sample data collected. In the first example, we have a sample of 9 data. We already know that the population is normally distributed, and the mean and the standard deviation are denoted by mu and sigma respectively. In part A, to estimate mu, we simply calculate the sample mean from the 9 sample data. Therefore, mu is estimated to be equal to 200. To estimate sigma, we need to calculate the sample standard deviation by considering n-1 as the denominator. Before we consider n-1, we can firstly calculate the standard deviation of the 9 data same as before. First of all, we can calculate the mean of squares. And then we consider the mean of squares minus the square of the mean. Afterwards, we multiply this factor n over n-1 to correct the bias in the estimation of sigma squared. As a result, sigma is estimated to be equal to the square root of 1725. With both estimated values of mu and sigma, now we can estimate the probability in part B. Therefore, the required probability is estimated to be equal to this normal probability. And so the answer is 0.3156. Finally, let's take a look at this example. In this example, there are 2 random samples taken from the population, and the information is given in this table. Now we want to combine the 2 samples into a larger sample with a sample size of 9. And then we need to use this combined sample to estimate mu and sigma squared. From the table, we only know the sample mean and the sample standard deviation of each sample, but we do not know the value of each datum precisely. So to find the sample mean of the combined sample, we need to consider the sum of data as 4 times 30.5 plus 5 times 29.6 like this. As a result, using the combined sample, an unbiased estimate for mu is 30. For the sample variance, it is much more complicated, as we need to consider the denominator n-1 in the original computation of the sample standard deviations of the 2 samples. By considering sigma square is equal to the mean of squares minus the square of the mean, we can get that the mean of squares is equal to sigma square plus the square of the mean. And sigma square is simply equal to n-1 over n times s squared. Because this factor n-1 over n can undo the denominator n-1 and make n the denominator instead. In this way, the sum of squares in the combined sample is equal to 4 times the mean of squares in sample 1 plus 5 times the mean of squares in sample 2. As a result, sigma squared is estimated as n over n-1 times the mean of squares minus the square of the mean like this. Thus, using the combined sample, An unbiased estimate for sigma square is 10.19. This is how we can perform point estimation for the population mean and the population variance from the collected sample data.